Hi ladies, so yes, I am not at work. My daughter needs to be watched and our babysitter's son is sick, so we can't send our daughter Ellie over to her, and my wife couldn't get the day off work, so I had to take it off. So, you're without a teacher, and I am still asking you to take notes, so you're probably grimacing about that a little bit, so I'm sorry. Show must go on though. We're near the end of the year. We don't really have that many classes left, and we have material we need to cover. So that's the reason I'm doing this. I'm going to just make one big video, and I'm going to go relatively quickly to keep the file size of the video down. So if you need to pause at any point in time to take notes, and then you can unpause it and pause it as many times as you need to make sure you understand what's going on, and also making sure you get all the notes taken down. As a way to say, I don't know if say I'm sorry or whatnot, but I did pull a couple pictures so I can show you my daughter a little bit. There she is. She's getting big. She's popping a couple teeth out. She is almost 6 months old, so she says she's sorry that she's keeping me home. Alright, but we are going to have some fun. And so here's the two of us. She's got a big smile on her face. She's great. I'll show you guys some more pictures later, but that's all for now. And now we really kind of have to get down to business. So, getting back here, we're going to work on properties of exponents today. Let me get a full page. Alright, so we have our properties of exponents, which is 5.1. And these are properties you've seen before. Everything you're going to see in this video, you saw in Algebra 1. So that's another reason why we're going to go relatively quickly, because it's just a little bit of a refresher. It's completely understandable if you don't remember everything, but at least something is going to look familiar to you. All right, so there are 7 properties which we're going to run through. And the first one is called product of powers. So we see the product of powers. In red are the quote-unquote formulas, and then in green you're going to see one example for each property. So we've got the product of powers here. So we have a raised to the mth power times a raised to the nth power. Anytime you have two bases that are the same and they're multiplied together, what do we do with their exponents? We add them. So this is equal to a raised to the m plus nth power. So an example that we have here is x to the 4th power times x squared. And so that is equal to x to the 4th power plus the 2nd power. And that's equal to x to the 6th power. The second example we have is called power of a power. So that's one base, a, raised to the mth power, and all of that is raised to the nth power. So we have one base, and it's raised to 2 powers. So what do we do with those exponents? Well, we multiply them. So that's equal to a to the mth power times the nth power. And we have an example here, x to the 4th raised to the 2nd power. So that's equal to x to the 4th times the 2nd power, which is equal to x to the 8th power. The next two, alright, the first one there is power of a product. So we have a base. It consists of 2 parts, a times b. So a is one part, b is the second part. That's all raised to the mth power. So what happens is this exponent gets applied to both parts of the base, or all parts, because sometimes there's going to be more than 2. There could be 3 or 4 parts even. So, but that, as long as it's all multiplication and division, that exponent can get applied, all right, to each part of the base. So that's going to be equal to a to the mth power times b to the nth power. We can't add the exponents here because the bases are different. Right, so all we can do is apply that m to both parts of the base. Then an example down here where it's x times y, this should be raised to the 4th power. x times y raised to the 4th power. So we're going to take that 4 and we're going to apply it to the x and we're going to apply it to the y. So that's equal to x to the 4th power times, not y, but y to the 4th power. All right, so x to the 4th power times y to the 4th. Another property deals with negative exponents. All right, so we have a to the negative mth power. Whenever you have a negative exponent, all right, you have to move the part that has that negative exponent. So it's either going to move to the denominator or to the numerator. It depends on where that negative exponent is. So currently we have a to the negative nth power, which is in the numerator, because this is like a to the negative nth power over 1. So to make this negative exponent positive, I literally grab this whole piece right here and drag it down to the bottom into the denominator, and that makes the negative exponent positive. So if you pull an entire numerator out, you need to replace it with 1. There's another scenario where we have the negative exponent, so this is OR, second scenario. The negative exponent is now in the denominator, so it's 1 over a to the negative nth power. I need to make this positive, so I'm going to pull it out of the denominator and bring it up into the numerator, and that exponent becomes positive. So we can do the same thing here with the variable x. X raised to the negative 2nd power, that's like x raised to the negative 2nd power over 1. So I'm going to grab this piece here, pull it out of the numerator, bring it down to the denominator, and the negative 2nd power becomes a positive squared. All right, so it's x squared in the denominator. We pulled the entire numerator out, so we replace it with a 1. Similarly, we have our OR, where we have x to the negative 2nd power in the denominator. Pull it out of the denominator, put it in the numerator, and we get x squared. The next property is called the zero exponent property. And that's stating that anything raised to the 0 power is simply 1. So a to the 0 power is 1. There's a stipulation here that a can't be 0. Anything other than 0 is raised to the 0 power is going to be 1. So x to the 0 power is 1, 10 to the 0 power is 1, 1 million to the 0 power, still 1. All right, and so we have an example here, not a million, but 100. 100 to the 0 power, that's simply 1. Quotient of powers. All right, quotient deals with division. All right, so we have the same base, all right, connected through division. What do we do with their exponents? So this is similar to the product of powers. So I'm going to take a moment, go back up. The product of powers, that was the first one that we saw. Product of powers, same base connected through multiplication. What did we do? We added the exponents. So you can think about it a little bit and ask yourself, okay, when you multiply two things together, what happens? Well, the product gets bigger. All right, well, what happens when you add two things together? Typically, you add things together to get bigger. So what happens when you divide? When you divide, the number gets smaller. All right? And so when you subtract, the number also gets smaller. All right? Typically. All right? So that's just one way to remember whether you're going to add or subtract. So this is going to be equal to a. This is a little bit too close, so I have to rewrite that. So a to the mth power divided by a to the nth power is equal to a to the m minus nth power. Where's my eraser? There it is. Minus nth power. And again, the stipulation is a can't be 0 because we can't have 0 in the denominator. Alright, so the scenario that we're going to work with is x to the 4th divided by x squared. So that's equal to x to the 4 minus 2 power, which is equal to x squared. And the last what was I going to say? Oh, yeah, the last property, that's the word I'm looking for. The last property is power of a quotient. All right, right, so here's power of a quotient. We have multiple parts to this base. Right, instead of connected through multiplication, it's connected through division. But the same thing occurs, all right, as we did with power of a power. Not power of a power, power of a product. Right? We have that m gets applied to both parts, gets applied to the a and to the b. So this becomes a to the mth power over b to the nth power. And the stipulation here is b can't be 0, because again, we don't want b or 0 in the denominator. So our last example here is x over y all squared. So that becomes x squared over y squared. And there's your answer. Okay, so these are the 7 rules that we're going to use as we run through a couple problems here. I don't need you to remember the actual names of the rules. I'm never going to test you on that. All right, but you do need to know how to use the different properties. All right, when you have to recognize when to use what. All right, but never will I ask you to say, tell me what the power, that you use power of a quotient or anything like that. So you never have to name the properties. All right, so we're going to look at a couple examples here, and you're going to see that there's actually multiple methods, all right, to get to the same answer. There's no rule that you have to necessarily use one property before the other. What I'm going to try and do is do these problems the most efficient way. There are other ways to do them, so if you notice, hey, why didn't you use this property? Probably just because it was a little less efficient. Okay, so if you have any questions, please note them down, like on the side of your notes, and you can ask me when we have class next, which will be on Tuesday. All right, so we have here evaluate numerical expressions. So I have 1 over 3 to the negative second power, all cubed, times negative 4 cubed. All right, the first thing which I'm going to do is I'm going to get rid of this negative power here. So I'm going to grab this whole guy from the denominator and move him up to the numerator. And it's going to become 3 raised to the second power, all cubed, times negative 4 cubed. Right, so essentially, once I brought this guy up to the numerator, there was a 1 up there. So 1 times 3 cubed is just 3 cubed. Next, I see I have power of a power. Right, so I have a base raised to 2 exponents. I need to multiply those. So I'm going to have 3 raised to 2 times 3, which is 6th power, times negative 4 raised to the 3rd power. So I've done all I can with my properties. Now I have 2 different bases. I can't add their exponents. The last thing I'm going to do is evaluate each number. So 3 to the 6th power is 729. And negative 4 to the 3rd power is negative 64. And all of that, when you multiply 729 times negative 64, you get negative 46,656. Second one, where we have 7 cubed times 7 to the negative 1st power. Same base, connected through multiplication, I can add the exponents. So that's equal to 7 to the 3 plus negative 1 power, which is equal to 7 squared, and 7 squared is 49. Third one, all right, we have 8 raised to the 0 power times 6 raised to the negative 2nd power. All of that is raised to the negative 1st power. What I notice is I have something raised to the 0 power. That automatically tells me that I have a number 1. Anything raised to the 0 power is 1. I have 6 to the negative 2nd power raised to the negative 1st power. 1 times 6 to the negative 2nd power is simply 6 to the negative 2nd power. Anything times 1 is itself. That's all raised to the negative 1st power. So now I have a base raised to a power raised to a power. What do I do with these? Well, I multiply them. So what's negative 2 times negative 1? That's positive 2. So I get 6 squared, and 6 squared is 36. Fourth one. All right, we have 9 to the 6th power divided by 9 to the 4th power. That's all cubed. All right, so I notice I have two bases that are the same connected through division. So what can I do with these exponents? Oh, I can subtract them. So that's equal to 9 raised to the 6 minus 4th power, all cubed. 6 minus 4 is 2. That's 9 squared cubed. One base raised to a power raised to another power. That's going to make this equal to 2 times 3. That's 9 to the 6th power. 9 to the 6th power is 531,441. Alright, so there's those 4 problems. All of these 4 problems included only numbers, no variables whatsoever. The next step is to add variables. So we're going to work with variables and we're going to work with numbers. So now instead of evaluate, we are going to simplify as best we can. So I have the product of k raised to the negative 3rd power times m raised to the 4th power, and that's all raised to the negative 2nd power. Since this is all connected through multiplication, what I'm going to do is apply this negative 2nd power to each part of this base. So I have a base raised to power raised to another power. I'm going to multiply those. So negative 3 times negative 2 is positive 6 times m. I'm going to multiply these two exponents. So 4 times negative 2 is negative 8. My answer is never simplified if I have an exponent that's negative. So only this part is negative though. Alright? The k has a positive exponent, so the k doesn't need to move. The only thing that needs to move is this m. So the k to the 6th power stays in the numerator. To make this a positive 8, I'm going to grab this m, bring it down to the denominator, and then negative 8 changes to a positive 8. And then I'm done. There's nothing more I can do because the two bases are different, so I can't combine those exponents. Second problem. Alright, I have the 3x divided by z squared all raised to the 0 power. All raised to what? All raised to the 0 power. Anything raised to the 0 power is what? 1. Alright, so you could simply just plop down the number 1. That would be the most efficient way. I know I told you I was going to do things efficiently, but I am going to break this down slightly to show you why. So again, there are 3 parts to this base. Here's the first part, here's the second part, here's the third part. When you have multiple parts to a base all raised to 1 power, as we did just in the last problem, you can apply that to each part of the base. Remember, when you don't see an exponent, there really is a little exponent 1 hidden in there. So what are we going to do? Let's apply this 0 to all 3 parts. So I have 3 raised to the 1st power raised to the 0 power. Multiply these two exponents. So 0 times 1 is 0. So that's 3 to the 0 power. X to the 1st power raised to the 0 power. Multiply 0 times 1. That's 0. So that's x to the 0 power. And then we have z squared raised to the 0 power. So 0 times 2 is 0. So that's z to the 0 power. And as we said earlier, anything raised to the 0 power is 1. So 3 to the 0 power is 1, x to the 0 power is 1, and z to the 0 power is 1. So 1 times 1 is 1. 1 divided by 1 is simply 1. So that's the longer way to do it, but if you notice that this was raised to the 0 power and that was equal to 1, and you just simply wrote 1, you'd be correct. Number 3. Alright, we have a string of 3 different parts here. So we have t to the 7th power times t squared times t to the negative 8th power. Notice all the bases are the same. All the bases are the same, all connected with multiplication, so I can simply add the exponents. So I have t raised to the 7th power added to the 2nd power added to the negative 8th power. So 7 plus 2 is 9. 9 plus negative 8 is 1. T raised to the 1st power is simply t. Number 4. F to the 5th power over g to the 2nd power. This should all be raised to the negative 3rd power. Alright, so two different bases. There's not much I can do here. I could move this guy up, but I'm not going to. I'm going to leave this guy where it's at. What I'm going to do is I notice I have two bases, each, so that's two parts, so actually one base. Alright, so each of these are going to see this -3, because that -3 can get applied to both parts of the base. So I'm going to take these exponents and multiply them together, take these exponents and multiply those together. So I have f raised to 5 times -3, which is -15th power. Down here I have g raised to the -2nd power times -3rd power, so -2 times -3 is the 6th power. So now this g is good, alright, since it's positive, it doesn't need to go anywhere. That g to the 6th power stays in the denominator. This f has a -15th power though, so we got to make that negative positive, so I'm going to grab this guy and drop it down to the denominator, and then the exponent turns positive. Remember, when we pull an entire numerator out, we have to replace it with the number 1. So our final answer is 1 over g to the 6th, f to the 15th. The fifth problem is y to the 7th, z to the 4th, divided by the quantity 3z raised to the -2nd power, all raised to the -1st power times z squared. So when you get these more complicated problems with division, what my rule of thumb is I try and simplify the numerator and the denominator entirely, alright, before I start working with simplifying numerator and denominator together. Alright, so I'm simply just going to look at the numerator first. Alright, I'm going to try and simplify this. And I see y to the 7th, z to the 4th. Different bases, can't add anything. Right, so there's really nothing I can do to that numerator. So I'm going to leave it the same. That's y to the 7th, z to the 4th. Now I'm going to look at the denominator. What can I do here? Well, I see I have a quantity with two different parts. Right, that's the z raised to the -2nd power is one part. This 3 is another part. All raised to that -1st power. So that -1st power is going to get applied to both parts of that base. So that's what I'm going to do first. Alright, so 3 raised to the -1st power is here, and I have z raised to the -2nd power times the -1st power, which gives me z squared. And I'm going to multiply that by this guy right here, which is also z squared. So the numerator, again, there's nothing I can do there, so I'm going to rewrite that. And I do notice, though, that I have two bases that are the same, connected through multiplication, so I can add their exponents. So I have 2 plus 2 is 4, so that's z to the 4th power. So I've got y to the 7th power, z to the 4th power, over 3 to the -1st power times z to the 4th power. Can't leave a negative in my answer, so the negative is part of this, it's attached to this 3. So I'm going to move this guy up to the numerator to make him positive. So I've got 3, y to the 7th, z to the 4th, over z to the 4th. So notice I did as much as I can here in the numerator and denominator before I started working with the numerator and denominator together. Alright, so in this step I was able to move the 3 up. Lastly, I notice I have z to the 4th over z to the 4th. Same base. Alright, same base, connected through division, so what do? I subtract. 4 minus 4 is 0. So I'm left with 3, y to the 7th, z to the 0 power, and z to the 0 power we know is 1, so that really can just go away. So these guys can cancel. Whenever you do the exact same thing in the numerator and the denominator, it can cancel, and your final answer is simply 3y to the 7th power. Last thing that we're doing, that we're done, alright, scientific notation. Alright, scientific notation you've seen before. Right, so we have scientific notation, which takes the form c times 10 raised to the nth power. And the stipulation is that c can go all the way down to 1, it It can equal 1, can't be below 1 though, and it has to be less than 10. So it has to be less than 10 and greater than or equal to 1. All right, in your final answer. If you see in your final answer that C falls below the number 1 or is 10 or greater, you need to move the decimal, all right, in order to have a quality final answer where our C value, which is the first number, all right, this is a C, this is a C, so that your C value is between 1 and 10. All right, and we'll see a couple examples of that, I promise. So here's a 3.5 times 10 to the 4th power times 1.2 times 10 to the 4th power. So we have two different examples of scientific notation connected through multiplication. Notice there's two parts to scientific notation connected through multiplication. So all I have here is multiplication. Multiplication, multiplication, multiplication. The commutative property can come into play here where we can regroup like terms. And I'm going to call like terms numbers that aren't 10. Alright, so all our C's are going to be like terms. So I'm going to group 3.5 and I'm going to multiply that by 1.2. And then I'm going to group these guys, 10 to the 4th and 10 to the 4th. So, straight line there. Alright, so there's 10 to the 4th times 10 to the 4th. So I'm going to multiply 3.5 times 1.2. Alright, and that's going to give me 4.2. So I have 4.2 times 10 to the 4th times 10 to the 4th is 10 to the 8th. Same base, simply add the exponents. My C value of 4.2 definitely falls within this range, so I can be comfortable with this answer. Alright, my C value is not less than 1, not greater than 10. Second example, very similar. We've got the one scientific number in scientific notation where it's 8.5 times 10 to the 7th. Second number in scientific notation, 1.2 times 10 cubed. Those are both connected through multiplication. So I'm going to regroup and say 8.5 times 1.2 and multiply that by 10 to the 7th times 10 cubed. 8.5 times 1.2, that gives me 10.2 times 10 to the 7 plus 3, that's 10 to the 10th power. So, here's an example where we have a C value that falls outside of this range here. Alright, so what do we need to do? We need to move the decimal so it falls within that range. So I need to take this decimal and move it to the left one. But by moving this decimal, it's going to actually change your exponent because you're changing the location, so it's going to be further away from its final answer in this case. So how do you change the exponent? I've taught this a number of times, and what seems to click with people is the concept of arrows. Alright, so if you're going to move the decimal to the left, the exponent has to go to the right. So essentially, there's arrows, and these arrows are always going in opposite directions. They never want to meet. If the decimal goes to the left, the exponent needs to go to the right, so the exponent needs to increase. If we were to move the decimal to the right, the exponent would have to go to the left, alright, always going in opposite directions. Alright, here they're going out, so they're either both going out or they're both going in, one or the other. In this case, they're both going out. So my final answer is going to be 1.02 times 10 to the 11th power. Let's look at a scenario where we move the decimal not to the left, but to the right. And that's going to happen when your C value falls below the number 1. And that's going to occur down here in number 3. So I have the number in scientific notation, 0.09 times 10 cubed. Second number is 10 times 10 squared. So I'm going to regroup and say 0.09 times 10. And that's going to be times 10 cubed. That's multiplied by 10 squared. So 0.09 times 10 gives me 0.9 times 10 raised to 3 plus 2 is 5. 0.9 times 10 to the 5th power. This number is too small, it's below 1, so I have to move this exponent over to make it larger. And remember, if I'm moving the exponent to the right, if I'm moving the decimal to the right, the exponent needs to move to the left, all right? These arrows always move in the opposite directions. So this becomes 9.0 times 10 to the, if we're moving this to the left, it's getting smaller, so that's 10 to the 4th power. So that's scientific notation with multiplication. We also have scientific notation with division. No grunting. These are the last two problems. All right, so same concept goes with division where you want to regroup. All right, so I have two numbers in scientific notation, 3.84 times 10 cubed, 2.4 times 10 to the 5th power. All right, I want to regroup, and it's nice, though, because I can simply just regroup like this. The numbers are stacked. So I've got 3.84 divided by 2.4. So I can divide these two numbers here, and I get 1.6 times 10 to the, remember, subtract these exponents. 3 minus 5 gives me negative 2. This will be my final answer. Unlike when you're evaluating and simplifying expressions, you can't have a negative exponent in your final answer. All right, with scientific notation, make a little note here. It's okay to have negative exponents when you're using scientific notation. Man, I can't spell exponents. There's an X in there. Okay, so it's okay to have negative exponents in scientific notation. Perfectly acceptable. Last problem. All right. So I've got 3.15. I'm getting ahead of the game here. Sorry. 3.15 times 10 to the 7th divided by 3.5 times 10 squared. All right. Again, regroup. Boom. So I go 3.5 divided, or 3.15 divided by 3.5 gives me 0.9 times, we have 10 to the 7th divided by 10 squared, subtract those, that's 10 to the 5th. That's pretty much the same exact problem we had before, we just reached it using a different problem. Alright, so we have 0.9, it's too small. Gotta move that exponent over to the right. Exponent, I said it again. Move the decimal over to the right. So I move the decimal to the right, exponent moves to the left. So that's equal to 9.0 times 10 to the 4th. So, I know that was a little bit of a whirlwind. Hope I didn't move too fast. If I did, hopefully you took advantage of that pause button. You now have some practice problems to work on. Whoever the sub is, they will assign them to you if they haven't already. You have the rest of the period to work on them, and whatever you don't finish is homework. Alright, so have a great weekend, and I will see you Tuesday. One more class and then spring break. Yay! Alright, so let's call it a day. Alright, we'll just kind of zip back over here, and you could see my daughter saying goodbye to you guys. Alright, and we're done. I'm out.